We'll move on to Robert Luxenhofer from Helsinki, who will talk about high-capacity polymeric micelles. I just noticed in the booklet that you're at the Institute of Sustainability Science. Be interested what that is. Maybe you can say one or two words about that. Robert?
Yeah, thank you very much for the kind introduction, and thanks to the organizers, Beat and everybody else, to give me the opportunity to speak here today. The HELSUS, the Helsinki Institute for Sustainability Science, is basically my secondary affiliation. Actually, I'm a Department of Chemistry, but basically it's an interesting interdisciplinary institute to promote sustainability in science in general, where Helsinki has a strong focus on. All right, so thanks a lot to Maria and Wim for perfectly setting me up. I don't have to explain polymer micelles anymore. And I introduced a new subtitle, in vitro, in vivo, and in silico. It took me many, many years to find somebody to model our polymers, all atoms in silico, because everybody told me it's not possible, it cannot be done at the moment, but now we actually did it. And I'm gonna be showing some data on this, and I think it could be really important for many of us to, in the future, also took in silico into consideration to understand what's going on. I'm starting with this acknowledgement slide. Basically, this is a long journey. The polymers took me from, I was just finishing my PhD in 2007, when I was in Munich, then to Sascha Kabanov in Nebraska, then to Dresden, then to Würzburg, and now I'm in Helsinki. So the micelles stayed all the time with me. And also a quick disclaimer, I'm co-founder of Delvacro Pharmaceuticals, that we want to bring this to the clinic. So we just saw polymer micelles, drug-loaded micelles, and basically our simplistic picture is exactly as we saw in the previous talk. We have a hydrophilic block, we have a hydrophobic block, and the drug goes to the hydrophobic block. And basically the hydrophilic shell or corona should stabilize, solubilize, provide stealth, and define somehow the protein corona. And basically, I think most people, if you look at the literature, just use PEG, or your favorite stealth polymer. When we look at the hydrophobic core, gives stability, Wim just said that, carries and protects the drug, and just make it PCl or PLGA or something hydrophobic. And to stabilize it, make it even better, just make it more hydrophobic or make pi-pi interactions. And I think this is too simplistic of a picture, and at least in our systems, we have good data to, and hopefully can show you that this is really not the whole truth. So our toolbox is basically polyoxazolines and polyoxazines, POX and POSI, how we abbreviate it, and you can see that you can have a wide range from very, very hydrophilic to very, very hydrophobic. We also have aromatic rings there. We can bring in, we can basically define so I'm a polymer chemist, we are polymer chemists in our lab, and we just design these from scratch. We make the monomers, we make the polymers. And basically for our drug delivery, we mostly use tri-block copolymers. We also did diblock, but they don't work as good in our hands with our systems. And for the hydrophilic block, we basically always use polymethyloxazoline. We will see later that we can also switch to polyethyl, both of extremely hydrophilic, similar to PEG. And from the hydrophobic, we synthesized a huge library of different polymers. I will not be able to show you the data on this, but there's tons of papers out there. These are some of the drugs we looked into. I think together with Sascha Kabanov, who's working with these polymers, we are now probably more than 100 or 200 drugs we looked into. Wide variety of structures. I would point out that Wim said, of course, many of these have aromatic rings. Very true, but many of these, and most of these, including curcumin and paclitaxel, they are very polar, actually. There are a lot of polar groups that are prone to hydrogen bonding. And I would argue hydrogen bonding is actually extremely important in solubilizing and stabilizing these formulations. So roughly from our experiments and together with Sascha's work, we see about that 30% of the drugs we observe drug loading of more than 30 weight% in our micelles. For many drugs, we get 50 weight%. So per gram of polymer, we get 1 gram of drug in solution. But the more important even is probably the amount that we can solubilize. So for paclitaxel, for instance, which is solubility of 1 milligram per liter, 1 milligram per liter, same actually curcumin, 1 milligram per liter. For both of these drugs, we went up to 80 grams per liter to 100 grams per liter with these micelles. So it's not only relative high drug loading, but we can get extremely high absolute solubilities with only the polymer micelles. All of this is published. And interestingly, for almost all drugs we test, we always outperform the standard pegylated, PEG-PCL, PEG-PLGA, or the standard carriers, let's say, the standard micelles. Sometimes there are others in the literature that get higher solubility, but it's relatively rare, I would say. And basically, I want to show you why we believe this is actually working that well in this system. So again, this is basically the platform. These are the papers we published on this. And I think the key thing is that our hydrophobic core is actually only barely hydrophobic. So in all cases, the micelles that have the barely hydrophobic core, like butyl, it is just on the brink of being hydrophobic, actually gives the superior drug loading. So we tried also aromatics, and we cannot get higher drug loading with aromatic or more hydrophobic systems. It's always the barely hydrophobic systems in the hydrophobic block that make it. And we believe it's because hydrogen bonding is trumping, thermodynamically, is trumping massively non-hydrophobic interactions. Okay. But very quickly, hydrophilic domain. So, okay, this was basically the hydrophobic domain. Now we're moving to the hydrophilic domain, actually what I actually want to talk about. So we're not the only ones looking into what happens actually in the hydrophilic domain. Martina Stenzel was publishing this in Angewandt, it's a viewpoint. And she is working and showed some clear evidence that the hydrophilic domain is interacting with drugs. It's not only the hydrophobic domain. And it basically can condense the hydrophilic domain. It can change the morphology of the micelles. Basically, it changes the packing parameters of the amphiphile. Therefore, it changes the self-assembly, maybe from spherical to warm or from warm to spherical. Many different things can happen. And we looked at this, for instance, with small angle neutron scattering. And what we also saw, and you can see that here in the red framed box, in the beginning, at relatively low 10, maybe 20 weight percent, we actually see that the curcumine, this is also curcumine in this case, actually goes predominantly to the hydrophobic block. But once you go towards 30, 40, 50%, and at 50 weight percent of curcumine in our micelles, there is more drug in the shell than there is in the core. Now, the problem is with SUNS, if you get your scattering data, after some time that you actually try to get beam time, you will ask 5 physicists and you get how to model that data, and you will get probably 100 different answers, and they can fight forever over it. I'm not a physicist, I can only listen there, but it's pretty frustrating for us because I don't know what is really the truth. Probably something in between, and probably many people have good aspects. But SUNS is really awesome, but it's really problematic also, I would say. So, but we are synthetic chemists, so my student actually, Heather, he had the idea then, well, why don't we just change chemically the hydrophilic block? We go from methyloxazoline to ethyloxazoline. We can do that. Would that do anything? And I said, well, both are super hydrophilic. I don't think it would do anything, really. I think the drug loading should be pretty much the same. So ethyloxazoline as a homopolymer is completely miscible with water. There's no solubility limit, right? Completely miscible with water, as is methyloxazoline. Now, when we combine it with in tri-block copolymers, again, we did these relatively hydrophilic or relatively polar butyl and propyl hydrophobic blocks. And again, methyloxazoline and ethyloxazoline is very similar to PEG in terms of solubility and polarity. So this is some data here on the drug loading. We can see very clear effects of our hydrophobic blocks. So on the bottom left, basically, you see different hydrophobic blocks: butyloxazoline, propyloxazoline, butyloxazine, propyloxazine, and paclitaxel and curcumine. And you can see that actually the butyloxazoline is the best one for paclitaxel, and the propyloxazine, which is the structural isomer, funny enough, is the best one for curcumine. But in both cases, we get drug loading of about 50 weight percent in solution and an increase in solubility in water of about a factor of 100,000. When we now change to ethyloxazoline, the drug loading drops to 20%, 25%. The pattern that we see in the hydrophobic block is still there. So the hydrophobic block does something, but the hydrophilic block clearly is involved and is important. So this was published in ACS Applied Biomaterials Interfaces. There's a lot more. We did mixtures, we did different hydrophilic blocks, so I don't have the time to go through that, although actually I'm pretty good in time at the moment. But I don't have the slides here, but it's in a paper. So a little bit in vivo work. So we've been talking about these ultra-high drug-loaded micelles for a long time, but I typically get the answer, so what? Like, does it really matter? Do we need this? I don't know. But we did some in vivo work. This was together with Sasha Kabanov. And basically here is just a comparison in a very, very simple tumor model. It's a xenograft, so nothing to write home about. But just showing here, we also compare to Taxol, we compare to Abraxane also, the other commercial formulation. And basically we outperform both. But this is from a pharmacokinetic study, and on the lower left side, you can see that with a single injection at MTD, and our MTD is about 7 times higher than the one of Taxol. So again, as Wim said, the paclitaxel injected in our micelles is much safer, much less side effects. So 7 times higher maximum tolerated dose. And with a single injection, we cured 4 out of 7 animals in both cases, but the drug loading makes a difference. So the dose you can see here we used is the same for both micelles. But 44 weight percent versus 29 weight percent gave a clear improvement in survival. And we were wondering for quite some time why this is. Same dose, same delivery system, different drug loading. And the higher drug loading seemed to be better. And now this is now a work very recently published from Sasha Kabanov. I'm not involved in this. Please have a read if you find this interesting. But what they found is also relatively recently, at high dose paclitaxel in our micelles, they basically use the same micelles that we do, as a single agent, it exerts a strong effect on the tumor microenvironment and uses long-term immune memory. So it seems that when you dose paclitaxel higher, very high, you actually get chemoimmunotherapy. So you basically get immunogenic cell death. And then they also combine it with a different drug, and read the paper. I don't want to talk about Sasha's work on his behalf. So, but now what I'm super excited about is in silico work, and this is the picture of Josef Kerain, the postdoc in my lab, preparing for the first Finnish winter. He didn't know what is coming, so that's why he's still smiling. So what Josef did, he basically took up the challenge to build these models and these polymer micelles in silico and do it all atom. So it's not coarse grain, which normally work in polymer micelle is coarse grained. But I said coarse graining is useless for us because I'm pretty sure hydrogen bonding is the key. And in coarse graining, you lose hydrogen bonding. And yeah, for me, it was clear we need hydrogen bonding, so we did all atoms. And the good thing is in Finland, we have really good computational resources, so we can actually do these micelles in all atom. We do reduce a little bit how many polymers we have in the micelle. We have an aggregation number of about 40. We think in reality it's more like 100, but the size of the polymer, they are full-size polymers. So the polymers are full size. The micelles have a slightly smaller aggregation number, but the drug loading is also as we have it in reality. And we have a lot of experimental data that we can now compare to what happens in silico. So he looked at these 3 different polymers that we saw before, propyloxazine with methyloxazoline as a hydrophilic block, with ethyloxazoline hydrophilic block, and butyloxazoline as a hydrophobic block. So for these, we have a lot of data with paclitaxel and curcumine. These micelles that we published just recently are with curcumine. We also are now working on paclitaxel. The computation is done, but we haven't analyzed the data yet. And we ran this to 2 microseconds. This is very, very long for these large micelles. And what we see basically is that the hydrophilic blocks, when we add the drug, they lose much more water than the hydrophobic blocks. The hydrophobic blocks, however, they are hydrated, in our case, probably not when we have super hydrophobic blocks like you just saw from Wim Hemming's work, but in our case, they are definitely hydrated. And I think it's actually important. And the decrease is more pronounced for the more hydrophilic methyloxazoline, which is surprising because it's more hydrophilic. It's more hydrophilic methyloxazoline, but it loses more water than ethyloxazoline, probably because it has more to start with. But very clearly, on the bottom right-hand side, you can see the hydrophobic core, it doesn't change basically upon drug loading, while the hydrophilic corona clearly changes. So this is hydration. Now Here, the polymer-drug interactions. Now we look at the how many drug molecules are around, or what fraction of the drug molecules is around the hydrophilic block repeating units and the hydrophobic block repeating units. And the amount of drug around hydrophilic monomers clearly increases with the drug loading for methyloxazoline, but not so much for ethyloxazoline. Now remember, ethyloxazoline is the one hydrophilic block that does not allow for high drug loading. But even in silico, it basically doesn't give the interaction. So it doesn't favor the interaction with the drug. So we kind of see in silico what we observe in vitro. And in fact, it seems to decrease, the amount of drug seems to slightly, but decrease around the hydrophobic monomer units. But this is probably the most interesting. So there's much more in this paper. If you're interested in this paper is massive, and there's a lot of stuff in there that goes much more into detail. And yeah, if you're interested, have a look. But here's just, I think, what is interesting is that the dynamics are also different. The dynamics of the interaction of the drug and the polymer repeat units are different between in the hydrophilic blocks. They're quite similar. You can see that on the left-hand side. Within the hydrophilic A blocks, the dynamics are very similar, but in the B blocks, we see clear differences in the dynamics. So the autocorrelation function goes faster or slower down between the butyloxazoline hydrophobic block and the propyloxazine hydrophobic block. And this basically shows how fast the hydrogen bonds are broken between the hydrophobic blocks, repeat units, depending on the nature of the hydrophobic block. So, and this actually correlates to spectroscopy that we published a few years before that. In the butyloxazoline, we see fluorescence. You see that on the bottom right-hand side. We see strong fluorescence of the curcumin, but we don't see it at the same concentration, same concentration of the drug, curcumin. We don't see the fluorescence. And that has to do with the molecular mobility, which we now believe we can correlate basically with the dynamics, how fast the hydrogen bonds between the polymer and the drug exchange. So we see, again, we believe a relatively nice correlation between spectroscopy and in silico. And with that, I think at least for our systems, we need to basically change our simplistic view of polymer micelles when they're drug loaded. I think there is a lot of evidence, not only from us, but from others, that the drug clearly interacts with the hydrophobic cargo. And just make it hydrophobic, at least in our case, certainly does not help at all. And micelles, drug-loaded micelles don't look like this. At least in silico, they more look like this. This is not, it's a messy thing, and it's a very dynamic thing. So in blue here, you see hydrophilic, in red, you see hydrophobic, and in green, you see curcumin. Okay, with that, again, I think there are profound interactions between hydrophilic corona of micelles. I think this is a critically overlooked phenomena that we haven't really studied much. And I believe, even more important, this is also important for protein polymer conjugates. This is important for polymer drug conjugates, I'm pretty sure. LNPs and liposomes. And now we do have computational capability to actually go for all atoms modeling of micelles, which is, for me at least, a game changer. So this was a very, let's say, fundamental report probably, but I hope it was still interesting for you. And with that, I come to the end and thank the guys who made that. I didn't talk about our NMR collaboration with Ann-Christine Pöppler. We also do a lot of advanced NMR spectroscopy with her. Also very interesting. Check out her publications. There is a lot of interesting stuff there. And with that, I thank you for your attention and yeah.
Thank you, Robert, for your very nice contribution, also from a different angle, literally taking a look at the micelles.